Fine. So this morning we will complete the analysis of the trajectory planning for the orientational part of the robot in the Cartesian space by making a comparison, an experimental comparison, in fact, between the use of Euler angles and the axis angle method. We have seen that separating the planning of for the position of the origin of the end effector, or for whatever positional component of the task you're planning motion, from the orientational part, we may either pursue, say, a strategy which is similar than that in the joint space, so designing trajectory for each component of a minimal representation of the orientation, just like we did planning for the single component in the joint space or the single component of the Cartesian space for the positional part. And this is one standard method. We have not shown anything about that because the procedure is exactly the same. If you have to make a reconfiguration from one initial orientation to a final orientation, you just associate to the initial orientation a desired, the set of angles of a minimal representation, Euler angle, roll PCO, whatever, and the same for the final orientation, and then you connect with any profile you prefer, linear, polynomial, and so on, in space, and then you assign a timing law. But we mentioned that this is not really visualizable in the sense that the orientation that the end effector will trace during this reconfiguration, it's not immediately clear. This is why we have introduced the axis angle method, which is exactly the same method that we have seen for describing orientation in general at the beginning of the course, but now we use it in a planning fashion. So we compute the relative orientation, we extract a unit axis which will be the invariant axis of rotation, and we plan a motion from 0 to the associated angle of the inverse axis angle representation of the relative rotation, and this angle will be traced with a given timing law. So the purpose of this experiment here, it's to show what are the possible different motion that you get. So we start for the KR5 manipulator, so it's a 6 degree of freedom revolute joint. We start with an initial configuration so that we don't have to care about inverse kinematic solution. This configuration is the one shown in the picture. You can see the word frame, which is nothing else, and also the base frame for the robot, so the 0 frame of the Navier-Tartenberg notation. The XW axis is horizontal and is pointing to the right. The ZW axis is vertical and is pointing along the axis of joint 1 of this robot. So the configuration, this configuration is associated to the values 0, pi over 2, pi over 2, 0 minus pi over 2, 0. So this is not really the full stretch situation, because the last joint, you can see it's horizontal. The fifth joint, sorry, it's horizontal. In fact, it's the minus pi over 2 here. If it were 0, then the tool, which is this gray object, which is used to support camera, in fact, for this robot, would rotate to the left and point with the long part pointing to the left, and the axis would point upwards. Okay, so this is the initial configuration. If we compute the direct kinematic in this configuration for this robot, sorry, we find the position P at time 0. So this is expressed in the base frame or in the word frame, and you can see the the red dot, which is exactly where we are locating the center of our last frame. So it's not really at the center of the flange, but it's at the end of this gray tool mounted on the end effector. Similarly, we can compute the initial orientation. Here, color may be not the best choice, but you can see the x-axis of the last frame in blue, the z-axis in green, and if you look at the orientation matrix at time 0, so r of 0, you can see that the x-axis is in fact aligned with the zw axis, and the z0 axis is aligned with the x-axis. This is the first and last column of the rotation matrix, which gives the directional cosine of this. So this is the initial orientation as well. And now we can extract from this matrix also the value of a set of, let's say, ZYZ angles. So we solve the inverse orientation problem in terms of these three angles, and we compute the value of these three angles, which are 0, pi over 2, and pi. So please stop me if something that I say is not clear to you, because at this stage you should this type of operation. It's the start. Why did we compute this? Because we want to compare what happened if we plan for this ZYZ Euler angles trajectory in orientation, or if we extract from the matrix R of 0 and from the desired target orientation a relative rotation, and from there an axis angle and an angle that we have to trace. So we will compare this. So first, let's specify the motion for position. As we said, we are separating the two things, and just to make things simple, we choose a straight path, so a linear path for position, and you can see the final point that should be reached at time capital T. We are not specifying yet this, because this will be the result of the timing law that we set on this path from P initial, so at time 0, and P final, so at time capital T. And you can see that it's a straight line. If you compare it with P0, it keeps the same height, ZW. It keeps also the same value of Y, so it's just a motion along the word x-axis from the beginning to the end. So this will be the final and effective position, and we specify also the final desired orientation. And you can see that this final orientation is pretty simple. So it's again specified by the directional cosine of the x, y, and z axis. I'm just reporting the x and y axis at the final time. So for instance, the x axis in blue again will now point downward to the with respect to the zw axis. So again, from this final orientation, we can extract a set of ZYZ angles. And if we plan the orientational motion with respect to this type of representation, we should move the first angle of this representation from 0 to minus pi. The second angle should not move at all, because pi over 2 should go to pi over 2. And the third angle should move from pi to 0. Okay? So this is the setup of the experiment. So here we will see the two videos of the resulting computation. I've drawn on the right-hand side the word frame in order to understand what's going on. Let's do some computation first. So for the ZYZ Euler angle, so we have extracted the initial and final value of phi. And for the axis angle method, we have extracted a unit axis, r, and a total angle that we should trace around this axis in order to get to the final orientation. So while we cannot say anything special about the change of the three angles, we can say something very clear. And in fact, our choice was on purpose simple, about the unit axis around which we have to rotate. So this rotation will be along an axis which is pointing like the y-axis, actually in the opposite direction of the y-axis, of the yw-axis, and will be a half rotation of 180 degrees, counterclockwise. So if from your point of view, the minus yw-axis or the r-axis here, you will see a counterclockwise rotation of 180 degrees. Of course, this can be interpreted also in the opposite direction. So we can rotate around minus r, which is 0, 1, 0, which is exactly the yw-axis direction. And then we would rotate by minus pi, so we would rotate counterclockwise. It's exactly the same motion. So this, we expect a very simple rotation for the second method. And in fact, in this particular case, this can be also previewed very clearly what's going on. I mean, the end effector will just rotate with respect to an axis, which is in the plane, which is normal to the plane where the robot is lying at this point. Okay, so let's see the video. So this is the rotation and the linear motion of the end effector using the linear path for position and a variation of the Euler angles from the initial value to the final value. Let's look at this again. So first, concentrate on the end effector, which is the center of this almost rectangular plate. And this is moving, again, this is moving on a linear path. The linear path doesn't change at all x and, y and z. So this is really a line with x. And this is why the whole body of the robot should rotate, retract, so that the end effector goes in line. And in the meantime, we achieve the full reconfiguration. So the final orientation is exactly what we expect. Now let's look at the other case. And you can see that the motion is completely different. In fact, the motion, if we look again at it, for the end effector occurs all in a vertical plane. In a vertical plane, so the linear motion is along the x-axis, and the rotation is around, as we have just computed, an axis which is normal to this plane. You can see that the final orientation and final position of the end effector is exactly the same. But the configuration of the robot is completely different. Why? Because we have planned different orientation in between with the two methods, and by solving this in the joint space, we get a different solution. Okay. In particular, again, let's look at this motion. You will see that there will be no rotation at all of three angles, in particular, no rotation of the base and no rotation of the joint 4, which is the first joint of the spherical wrist of this robot. Whereas, let me see if I can catch this again. Whereas you can see that all the joints will move for this motion. Now, this is a special case indeed, but I picked this example in order to show clearly the differences. Sometimes you don't see the difference so clearly, but what you can see clearly is once you have computed the unit axis, which is invariant for the orientation, then you can localize immediately this axis in space and then understand what will be the intermediate value. Okay, let's move to the next slide. Now, these are it's a comparison of, well, the full trajectory. So this is the linear part, in fact. On the left-hand side is the Cartesian component of position and velocity. And you can see that there are no apparent changes because the positional part is executed in the same way. However, if you look carefully, there is a difference. So on top, you will see the x, y, z component. And in fact, you see only a motion in the x direction. So the green y and the red z value will stay constant. At the bottom, you see the velocity that you have achieved on that path, so the linear velocity. Again, two velocity are zero, so you see only a red line because this covers also the green line. You see only a velocity, which is a triangular one, in fact, for the x coordinate. And you can see also that values are different, but more than that, the motion is completed in two different times. Why is that? Any suggestion for this? So here we see that we can complete the motion using the axis angle method sooner by 1.2 seconds, so almost 15–20% faster than the 7.2 seconds that we achieved using the Euler angle. Why is that? I'm expecting verbal or textual suggestion from home. In the axis angle method, maybe we don't have coordinated motion between all joints. Well, that's not the case. That's not the case because we follow the same, if you remember the other example that we treated last time, we give a timing law for all components at the same time. So we give a timing law S of time between 0 and capital T, and this S maps into the linear path, which is parameterized by S, or in the angular part of the axis angle method, which is an angle parameterized by S, which goes from 0 to the full rotation needed, or in each single component of a linear path parameterization for the three angle. So coordinated motion occurs. In fact, if you have looked carefully at the video, some joint didn't move at all, but all the joints that moved started at the same time and ended at the same time. So it's a coordinated motion. And there's a single timing law. So you have to remember what we did in the first example where we just used the Euler angles. We set up a problem in terms of the timing law. So for a scalar, this scalar function was chosen as a trapezoidal profile, keeping into account a maximum acceleration and a maximum speed, both for the linear and the angular component. And then, since the displacement of each coordinate for x, y, z, and for the three angle of the Euler representation was given, we made the computation with this, like we did for the trapezoidal case. And in fact, we find out, because of these plots, we can retrospectively say that we were not able to reach the maximum speed because before reaching the maximum speed, we decelerate. So this is a subclass of the trapezoidal speed profile, which collapses into a triangular profile. And computing the slowest solution, I mean, we fix this as the total time, and this happens to be 7.2 for the Euler angles and 6 for the axis angle method. Okay, so this is what was specified by this additional text. So we imposed the previous bound on angular motion. Again, that were the most binding part of the constraint. Of course, if you play around with those bounds, so V max, A max, something on omega max and on omega dot max, so linear and angular velocities, linear and angular acceleration as a scalar, of course you may end up with other solution, but what is to be understood here is that probably the required motion for the three angles of Euler angles are larger than what is needed by the single angle rotating around the invariant axis for the axis angle method, and this imposes this limitation. Okay, now let's look at the orientational part. In fact, you can see on the left side, in 7.2 seconds, now these are plots over time, how the triangle changes. There was the second angle of the ZYZ representation that did not have to change. It's going from pi, I think it's 1.57. So it's pi over 2 remains constant pi over 2. These were the initial and final values, so there was no change for this, while you can see again a profile, smooth profile for alpha and gamma that goes from their initial value to the final value. Now pay attention, on the right-hand side, I'm reporting what would happen if we had used, I mean, with the resulting motion of the axis angle method, if we compute on that motion, what is the associated value of alpha, beta, and gamma? So you can see that alpha, beta, and gamma here are changing in a smooth way, while in the other situation, we would have a very strange phenomena. We would have the second angle getting into a singularity. In fact, beta equals 0 is the singularity of the representation. In fact, we have not planned the alpha, beta, gamma in that way. We have planned them in the left-hand side way. So this was the planning for the triangle. On the right-hand side, we planned a rotation around the invariant axis of the axis angle method. Indeed, for every intermediate orientation that we get, we could extract the three angle of the ZYZ representation, and that would be the profile. You see, constant angle for 2 for some intermediate motion until the half of the motion, in fact, until 3 seconds, while the beta angle would fall down to 0. And falling down to 0, this would be the singularity. You know, if the second angle is not rotating in a ZYZ or ZXZ or the other 4 representation in which the first and the last axis are the same, when the second axis, there's no rotation around the second axis, indeed, the first and last axis align, and this is a singularity because we don't span the whole three-dimensional space with the 3 axes of rotation. This should be clear at this stage. So we see that we would have encountered a singularity in that case. And when we get out of the singularity, we have a switching of the values because of how we are computing things. In fact, we always have 2 solutions. So we enter with one solution and we exit from a singularity with another solution, which is pi. In fact, the red line goes from pi to 0, the blue line from 0 to minus pi, while beta recovers an intermediate value. Okay, so this is just post-processing. So if we had planned with Euler angles this type of motion, we would have had a problem in terms of singularity. So the resulting joint velocity would have exploded somehow if we were tracing that kind of orientational profile. So this is in fact the actual joint motion, which was obtained by inverse differential kinematic, in fact, and then giving this velocity command to the robot, and then collecting from the robot the encoder measurement. And these are the plots of the encoder measurement. And as expected, on the left-hand side, we see all 6 joints moving. In fact, they are changing. They are different color. You can trace what are this according to the previous video. While on the right-hand side, again, in 6 seconds plus something, and here 7.2 seconds plus something, because as I said, and as we will see next, we need to close a Cartesian control loop on the error to recover the approximation that we introduced because of the slow update of commands that we were realizing. And in fact, we are realizing this slow update of commands because we are using the robot interface with our external program, and we can receive data and upload new commands only every 12 milliseconds. And this delays gives some problem in executing correctly the trajectories, which would be different if we could access directly the low-level control loop. But in any case, the difference between the 2 sets of joint motion is very clear. In the second case, only 3 values are there. All the rest are the light green line staying at 0, so not moving those joints, which remains at 0. So only 3 joints are moving. In fact, the joints that will achieve a motion in the vertical plane where the robot is standing. If you remember the video, this should be very clear. Okay, any comment on that? Okay, so let's move on and conclude this block of slide by presenting a property which in fact can be applied to any trajectory, no matter if in joint space or in the Cartesian space, okay? So it's here just because it concludes the whole block of trajectory planning, which is called uniform time scaling. What is this? Okay, suppose that we are given a path, and now I'm using the P as it was a position in the Cartesian space, but in fact it could be anything, so in joint or Cartesian space. And we have chosen a timing law on this path, so we have a full trajectory. And we have scaled the time with respect to the total motion time. So we have a function s of tau, where tau is t over capital T. You can do this scaling or not, but I think that this is clear enough. So we are moving the robot globally, so in joint Cartesian space, everything is moving no matter where we plan this. And the total motion, let's say it's a rest-to-rest motion, for instance, lasts t equal 2.5 seconds. Now we may need to check at the planning stage before executing the robot if this is a feasible motion. So if we don't violate the limit that the actuator can produce, or that the task is imposing to us. So there could be bounds on the velocity and or on the acceleration. And this could be bounds in the joint space. And if these bounds are in the joint space, they are limitation of each joint motion, which is associated to the capability of the actuator that moves that joint. If instead these limits are in the Cartesian space, well, it is hard to map the limitation in the joint space to the Cartesian space, because this may depend, as we know, on the configuration, because there's a mapping, for instance, in the velocity case, the joint velocity are mapped into the Cartesian velocity by the Jacobian. The Jacobian is a function of Q, so even if we have constant bound in the joint space, we will have configuration-dependent bounds in the Cartesian space. So most of the time, this bounds, this limitation in the Cartesian space comes from the nature of the task. So for instance, if we are doing a circular path, so if we're moving at constant speed, we will have a centrifugal acceleration, and maybe we will limit this centrifugal acceleration, which would impose a limit on the Cartesian speed through which we are tracing this path. So no matter where these limits and bounds are coming from, we have to check if our trajectory is feasible or not. Now, there are cases in which this check is not needed because at the level of planning, we have already taken into account this limitation. For instance, if we do a trajectory in the Cartesian space on a straight line and we use a bank-coast-bank acceleration, and in the bank-coast-bank timing law, we are already taking into account the Vmax and the Amax. Of course, by construction, I would say, by design, we have satisfied this limit. Same if we are planning this motion in the joint space and we have a trapezoidal velocity profile, or which is equivalent to a bank-coast-bank acceleration profile. And in doing this, we have taken into account the limit at this joint. And if we have done a coordinated motion, then we have slow down the fast joints so that they complete the motion at the same time as the most burdened joint, burdened because it has either less capability in terms of motion, or it requires to move a longer path than the other joints, okay? Or if we have just moved independently one joint at a time, but each joint has satisfied this limit, so we don't have to check this afterwards. But in general, we have planned the trajectory for other reasons, maybe not taking into account this bound. And now we discovered that either the trajectory is unfeasible, or it's very slow, too slow for what would be the capability of the robot. So we could decide to scale uniformly time, so that, for instance, if the trajectory was too fast, 2.5 seconds was too fast, we would like to reduce, for instance, to 1.5 seconds or to 1 second. Sorry, exactly the opposite. If it was too fast, so we would like to move from 2.5 seconds to 4 seconds, 5 seconds, 10 seconds, and so on. So just modifying the total motion time, it means that in the meantime, we are following the same type of profile, but scaled over time. Vice versa, if we realize that the 2.5 second was too slow with respect to the capability of my bounds, so I'm really well within the bounds, I would like to speed up motion and reduce from 2.5 seconds of total time to, let's say, 2 seconds, 1 second, 0.5 seconds, and so on. So it's not a matter of trial and error. There are properties connected to the kinematics, and we will see that similar property will hold also when we're dealing with dynamic models, so considering inertia, gravity, centrifugal and Coriolis phenomena, inertia of the link, and so on. So this property says that if we scaled uniformly, so we just stretch or compress the total time, then we will have a linear scaling of the velocity. And this is because if we compute the time derivative, so with respect to the natural time of our motion, so p dot or dp over dt, and s is a function of tau, tau is a function of capital T, sorry, of t with a factor of capital T. So we do the chain of derivative. So we have dp over ds, ds over d tau over dt, which gives a factor 1 over t. So if we double capital T, we will halve the velocity at any time, because all the rest remains the same. If we halve the total time, we will double the speed at any instant. Of course, the interval is longer or shorter, but if we map the single sample of the velocity with respect to the original one, they will be either doubled or half if we choose to double the time or half the time. Okay, pay attention. It's the reverse. Okay, so this is a very nice property, but even nicer, if you wish, or maybe not unexpected, is what happens to the acceleration. So we take the second derivative with respect to time. We do the operation, and we can see that we can factor out for the two terms that will occur, a factor 1 over t squared, because it's a factor 1 over t within the ds d tau over t squared in the first addend, and there's a factor 1 over t squared in the second derivative of tau with respect to of s with respect to time, which converts into this factorization. So this means that if we double the duration of our motion with respect to the original one, we will have a factor 1 over 4 to the acceleration. So all the acceleration will scale down by a factor 4. And if we halve the duration of the time, all the acceleration will get up by a factor of 4. Okay? So, and in fact, this holds also for higher order derivative. If you have a limitation on jerk and you scale uniformly by a factor k, larger than 1 means slowing down the motion. Smaller than 1 means compressing the motion. Then this factor will be scaled by the cube in terms of resulting jerk. So this is summarized by this concept. So these two properties, and whatever higher order differential property you want to use, will induce a simple way in which to scale the minimum or the maximum that you would like to do in order to become feasible in the limit. What do I mean by that? So if the motion is unfeasible to start with, so the trajectory that you have planned, then you want to scale time, in fact, increase time. So move from capital T, the original total motion time, to k time t with k larger than 1. And this k will be dictated by the most violated constraint. So if you're looking at the absolute value of speed and acceleration, and this can be replicated on several joints, on several components of the Cartesian. So you have many ratios to consider, and then you take the maximum one. At least one will be violated, so will be larger than 1, and then you scale by this factor, okay? Or by the square of this factor is the violation, is on the acceleration because of the previous property. If the motion is too slow, it means that all these bounds are largely satisfied, so you want to speed up motion in such a way that velocity are scaled linearly, so will increase linearly. Acceleration will increase quadratically with your factor k, but at some point, one of this will touch its bound, and then you have to stop. So this computation can be done without trial and error, but just looking at the formulas, okay? So in both cases, after the scaling, there will be typically one, but at least one in general, instant of saturation. So one variable, either of the velocity type or of the acceleration type, will reach its limit, or the one that was violating, most violating, will be at the boundary, and all the other, violating or not, will be lower. So we don't need to recompute the motion profile from scratch. We just take whatever we have, and we scale the things properly. So let's do a numerical example that everything will be clearer. We take our good old friend, the 2-hour planar robot, unitary link, why not? And suppose that the path was a linear path. So we are now doing the scaling in the Cartesian sense, connecting an initial configuration Q0, which is in light green here on the screen. Associated to this configuration by direct kinematic, we have a position P0. And we would like to get on a straight line, so a linear Cartesian path, to a point P1, which we specified as 0.816 and 1.4 in the plane XY. And you can see this. And we design on this path a cubic timing law in 1 second. So it's a cubic timing law, probably rest to rest. So it starts from 0 velocity, goes to 0 velocity at the end, and you can compute at this time the two coefficients, -2 and 3, if I remember, higher order terms. The lower order, so the linear and the constant part of this cubic timing law are 0. So just refer to the cubic trajectory, no, the scalar cubic trajectory in the joint space. We have used the formula there, but you can apply it as a timing law as well. And the total time is 1 second. Okay. So if we do this planning, the parameter s with respect to time will have a cubic profile in 1 second. It will go to 0 to the path length L, which is nothing else than the norm of the difference between P1 and P0, so the length of this linear segment. Because of the boundary condition 0, so the S dot will start from 0 and end at 0, so it's a rest-to-rest motion, and the peak at the center can be computed in closed form is about 3 meters per second. And of course, the acceleration profile is linear, so you start with a maximum acceleration, you decrease this acceleration constantly, you get to 0 acceleration where the velocity has a maximum, so at half the motion, so at time 0.5 second, and then you get to the symmetric negative deceleration where you stop. Remember that in the interval 0 capital T, so 0, 1 second, excluding the boundary, you have continuity of up to the acceleration. While you have a discontinuity, because if everything was at rest before, so even the acceleration was 0, to a value which it's about 12, I would say, at the initial time, at the final time, you jump from -12 to 0 again. So there's a discontinuity in the acceleration in this case. If you don't want this discontinuity in acceleration, you should have planned a timing law which is, for instance, a quintic rest-to-rest timing law, imposing also acceleration 0 at the beginning and at the end. Okay, so now suppose that we have bounds in the joint space. Pay attention, we have planned a motion in the Cartesian space, so I'm using this exactly as a combination of all the possible things that you can do. Again, you will find in the exams, in the list of exams, in the exercise, many other situations. You can really play around with this unendlessly. So I've chosen a limit in joint speed, so a Vmax1 for joint 1, 2 radians per second, Vmax2 for joint 2, 2.5 radians, and same for the acceleration of the two joints, and these are expressed in radian per second square. So what should we do? We should take this Cartesian motion, and from this Cartesian motion we have the position, and so for each position we do inverse kinematic and we have the associated configuration, and we will keep always one of the two solutions because we start with elbow up, and now even the final solution, as you can see, the stroboscopic tracing will be elbow up, although this is reversed, so it seems elbow down, but in fact we never cross the singularity. Okay, so we start with that for each position on the path that we sample, let's say with 100 samples or 1,000 samples if you wish to have more accuracy. So for each of these we compute the configuration. Then we have indeed also the p dot, so the Cartesian velocity, which is nothing else than dp over ds, so p prime times s dot, and here you can see the s dot profile is this quadratic profile with a peak at 3 meters per second at the midpoint of the trajectory. And then you invert this velocity with the Jacobian, so you have j to the -1 of this velocity, and you have the q dot, and you check if the q dot over all the path satisfy the bounds, And then you move to the acceleration, so you need to compute p double dots. This will include p prime and p double prime. It will include s dot square and s double dots. The s double dot is the linear profile. So you have everything you need, not just graphically, you have it analytically to compute also the Cartesian acceleration, and then to invert the Cartesian acceleration into a joint acceleration, inverting the Jacobian. You never cross a singularity here, so you can always do the standard inversion, and taking into account also of the j dot q dot term at the second order level. So if you do that, you obtain this type of evolution for joint 1 in red and for joint 2 in blue. And I haven't put any limits on the joint range, but if I had violated some joint limits in terms of angles, then no matter how I speed up or slow down the motion, I will trace again the same joint path, because I'm tracing again the same Cartesian path, and there's a unique solution in the inversion. So time scaling works only on potential violation or large satisfaction of limits at the differential level. So this is just to show this evolution, and the total time is 1 second, as we said. And now in the second plot, you can see that there are dashed horizontal line in red, limit of velocity for joint 1, which is largely violated on the negative side, not on the positive side, and a slightly larger range for the joint velocity 2, and again also the second joint velocity is violating in a different instant, and again on the negative side this bound. If we look at the acceleration profile, you can see that joint velocities start from 0 and end at 0, because this is a rest-to-rest motion. If the Cartesian velocity is 0, then also the joint velocity will be 0. This is not true for the Cartesian acceleration, which see they start from different from 0, and therefore also the joint acceleration start and end at values which are different from 0. But apart from this, you see that the acceleration limits are wildly violated in several instances. So the first joint violates right from the beginning, and also the second joint. This bounds and then remains outside the bound, first on the negative side and then on the positive side, and then again on the negative side at the end, while positive and negative positive violation for the blue plot, which is the acceleration of joint 2. So this is a largely unfeasible motion. The time 1 is way too large. Now what we do, we look at the maximum value of the joint velocity 1 in absolute term, the maximum value in absolute term, the maximum value in absolute term of joint 2. We compare this value with their limits, and we see what is the most violating one. And this will give a tentative time scaling factor k. We do the same for the acceleration, so we take the maximum value. You can do this while you're generating the trajectory. You keep trace of what is the maximum value in absolute term. For the red and the blue acceleration, we compared them with their limit A max. Of course, these are symmetric limits, so you just compare the absolute value of this acceleration. And again, this will be a factor, but remember that this factor appears with a square term. So if you do this, the relative maximum variation in velocity, you get a k-val, which is 2898, which is the maximum between these three numbers. The 1 in first position means that if k-val, if all the joint velocity at any time during this time interval of 1 second remains within the bound Vmax1 and Vmax2, these two numbers, the second and third number in the first expression, are less than 1, so the maximum of these three is 1. So this will induce no need of scaling as concern the velocity. Now, you do the same computation for the acceleration. You see that the factor is much larger in this case, because the violation is much larger. And in fact, the ratio, now on the plots, you can see that there are two different instants. One is around 0.32 seconds for the velocity, and the second one is around 0.42 seconds, and this will be the maximum instant of violation of the acceleration. And now you have to choose what is the k by which you have to slow down in this motion, okay? So the minimum scaling, the minimum means that, of course, you can scale even more, but then you would be too conservative. In order to recover feasibility in this case, because we were exceeding the bounds, is the maximum between the k1, of course, you always keep this for safety, the k-val, and the square root of k acceleration. Because you know that you scale by in a quadratic form the acceleration. So if you do this computation, it will be, although the absolute value, the value of kx was larger, but if you take the square root, this becomes smaller than the limitation of velocity. So stated in a different way, it's the velocity bounds that is the most stringent one, the most violated in terms of relative to their limits. So this computation gives that k 2.898. So we have to slow down by a factor of about 3 the motion. And then if we do this, we will have a scaled timing for the Cartesian path. So the first three lines are exactly the same plot that we showed at the beginning. And the duration now, you see that on the x-axis we have time, and now it's almost getting to 3 seconds. And in particular, if you look at the central top plot, this is the speed on the Cartesian path. You remember that the peak was about 3, and now the peak is around 1. So we have scaled by the factor k that we have chosen, the Cartesian speed. And of course, same story by a factor k squared, so by a factor about 9, we scaled the acceleration. In fact, you can see that it's around 1.4. We had 12 or 13 to start with. So this is the scaling on the Cartesian trajectory, and of course also on the joint motion. The first plot in the second row is the actual joint motion, which has not changed at all. So we are tracing exactly the same configuration, but now at scale time, because we complete the motion not in 1 second, but in 3 seconds. So these are exactly the same plot as before, but now, stretched in order to reach the final configuration at the new time, which is t scaled about 3 seconds. While if you look at the joint profile of velocities, you can see that the joint velocity 1, at the instant where it was the most violating one, now it's touching its boundary. All the other instants, that velocity and the velocity of the other joint satisfy the bound. And same for the acceleration, which are being reduced within their bounds. There's one instant of one variable which is at the maximum speed in this case. It could be instead the most violating constraint would be an acceleration, then it would be that acceleration component that would have been brought back to the value, to the limit value. So just a last comment. Of course, you could do better than that. You could do better than that in the sense that you can recover feasibility, but completing the motion not in about 3 seconds, but maybe in 1.2 seconds, so much less than the original one. How is that? You could, in fact, use a non-uniform scaling of time, so to compress the time where you had enough space in terms of velocity and acceleration capability, and delayed time in the instance where you were violating things. So this non-uniform scaling becomes an optimization problem. It can be done, but it's a much more tough problem. In that case, you would get smaller times for feasibility, and vice versa if you were too slow you can be much faster if you increase time, but not uniformly, okay? I think that this completes this part. So there are a few comments on this. And